topic. See the topic electrochemistry, session 1. The learning objectives are: first, recognize the conductivity of electrolytic solution. Second, define the terms resistivity, conductivity, equivalent and molar conductivity. Next, factors affecting equivalent conductance. Now introduction. In our regular life, real life, we used a lot of electronics items in my house, appliances and gadgets. So their components are made from the electronics components manufacturing from conductors, semiconductors and insulators based on their electrical conductivity. This is the main concept of this lesson. Now, next point, you might have noticed that the conducting materials such as copper and aluminum etc. are used to transport electric energy from one place to another place, and the insulating materials such as PVC. PVC means polyvinyl chloride, backlight in switches, circuit boards etc. In electrical field, you know that the electrical wires are used to transport the electrical energy from main box to the appliances, and then for our safety purposes we used PVC plastics and backlight plastics for switches and circuit boards also. So what is the purpose of these components, and then how to generate the electrical energy? In this lesson we see this concept, electrical energy, how to generate. Okay. Next, we know that the first law of the thermodynamics, this is the basic for this electrical energy and any other energy. The law of thermodynamics, the energy can neither be created nor be destroyed, but the form of energy can be converted to another form. This is most important basic in thermodynamics. This is the first law of thermodynamics. Again I will tell, the energy can neither be created nor be destroyed, but one form of energy can be converted to another. This means any type of energy we cannot create or destroy. They already there in our universe. So, but one form of energy can be converted to another form. They cannot create or destroy, this is the point, but the energy can be converted to another form. Can be converted to another form means how we used a lot of energy system, manufacturing energy system. One is water energy, next solar energy, wind energy, tidal energy, and then thermal energy. So many energy we have manufactured from the natural sources to our users, home appliances users, and then commercial users also. So in such a way, the converting chemical energy also converted to electrical energy in case of batteries. Batteries also we used. In batteries, the chemical energy is converted to electrical energy. So, this is the basics of this energy. Now, the image is the wire and inside the wire the metal, copper metal, and then components. Third images, various components in electronics, IC, resistor, and then capacitor, so many op amp, and then transistors also. These are the components in electronics field. Okay. Now, next point. We cannot image modern technological world without batteries. Without batteries we cannot survive in our recent new technological view, because batteries is the very important source for movement of vehicles, mobile users, and then home users also. The battery is very important. Okay. Next, it is important to know that the principles of behind the type of energy conversion. What are the principles for energy conversion? We see in this lesson. We see in this lesson the basic branch of electrochemistry. What is electrochemistry? This is the definition. It deals with the study of electrical energy transport, and the interconversion of electrical and chemical energy is called electrochemistry. This is the definition. The study of electrical energy transport and interconversion of electrical and chemical energy is called electrochemistry. Very important 2 mark. Next, electrochemical reactions are redox reaction. Electrochemical reactions means the conversion of one energy to another energy, that is electrical energy to chemical energy. The redox reactions takes place. Redox means, what is redox? Reduction and oxidation reactions are attained at a time simultaneously taken into through the chemical reactions, reductions and oxidation. That is called redox reaction. They involve the transfer of basic principle for this is the movement of electron from one substance to another. This is the redox reactions. That is conductivity, basic principle for conductivity, the transfer of electron from one substance to another substance. In this unit, we learn about the electrical conductance, construction of batteries, and thermodynamic principles involved in electrochemical. In this unit, we will see that. Okay. Next image is the electrical appliance, bulb through wire. This is battery. Okay. Now, next, conductivity of electrolytic solution. The topic is electrolytic solution. We have learned that when an electrolyte such as sodium chloride and potassium chloride etc. is dissolved in solvent like water, the electrolyte is completely dissociated to give constituent ions, namely cations and anions. In chemistry, in lower classes, we already seen that, know that sodium chloride or potassium chloride, any salt dissolved in water, they split, they decompose it, positive ion and negative ion. This is called electrolytic solution. So, electrolytic solution. Okay. Electrolyte, that is called, the sodium chloride and potassium chloride called as electrolyte. when an electric field is applied to such an electrolytic solution, if electrolytic solution means sodium chloride or potassium chloride is dissolved in water, they act as a electrolyte. We passed the current to the solution. The ions present in the solution carry charge from one electrode to another electrode, thereby they conduct electricity. How they conduct electricity? The movement of anions to cations, anions to cathode, and cations to anode. The movement of ions in electrolytes. This is the concept. Okay. Next, the image, the cell, various cells, two types of cells here. Next, the conductivity of electrolytic solution is measured using the conductivity cell. The conductivity of electrolyte measurement using conductivity cell. Okay. The conductivity cell consists of two electrodes, one positive and negative, immersed in electrolytic solution. Without electrolytic, they can't pass the current from one electrode to another electrode. So, electrolytic solution is very, very important. It obeys Ohm's law. Ohm's law, like a metallic conductor at a constant temperature. This is the condition. Constant temperature, the current flowing through cell is directly proportional to the voltage across the cell. This is the Ohm's basic principles of Ohm's law. At constant temperature, the current flowing through cell is directly proportional to the cell voltage of the across the cell. This is the basic principle. You see that I is directly proportional to V, or I is equal to V by R. I is the current, V is the voltage, and R is the resistance. Therefore, V is equal to IR. This is the most important rule in physics and electrochemistry also. V is equal to IR. How to I is equal to V by R, voltage, resistance, and then current. Okay. When R is the resistance of the solution in Ohm, the resistance is the opposition that cell offers the flow of electric current through it. The concept R is the resistance opposition of the cell offers to flow of electric current through it. This is very, very important. What is R? Okay. Next, resistivity. Resistivity, the letter represented by rho. Let us consider the conductivity cell. Conductivity cell means used for measurement of passing through current. Conductivity cell, which is the electrolytic solution, is confined between the two electrodes having cross-sectional area A, and are separated by the distance L. Separated distance L. L. This is a very important in formula, resistivity formula. A and L. A is the cross-sectional area of the electrode, and then this L is the distance of the two electrodes. Like the metallic conductor, the resistance such an electrolytic solution is also directly proportional to length and inversely proportional to cross-sectional area. This is a very, very important relationship, directly proportional to length of the electrode and then inversely proportional to the cross-sectional area of the electrode. This is the basic concept. Okay. Now, see the diagram. Rho is the resistivity. We want to measure the resistivity. L is the length of the electrode. A is the cross-sectional area, means the circular wire means the circle area. Okay, A is the cross sectional area. Next, resistance R is equal to rho into L by A. Rho into L by A. Rho is the resistivity, L by A. R is the resistance of this particular electrode. Okay. Now R is equal to L into rho into L by A. Rho is the resistivity. Now R directly proportional to L by A. R is equal to rho into L by A. So this is the formula for resistivity. Rho is called the specific resistance or resistivity, which depends on the nature of the electrolyte. Nature of the electrolyte means the nature of positive ion and negative ions, that is anion and cations, how to move, which resistance, which metal, type of metal, also all are the important characteristics. So rho is the specific resistance which depends on the nature of the electrolyte. Electrolyte means you know that sodium chloride, potassium chloride, or any salt with dissociated in water. Okay, this is called electrolyte. Okay, if L by A is equal to 1 per meter, L by A is equal to 1 per meter, then rho is equal to R. So the resistivity is defined as, this is the important 2-mark question, this in what is resistivity? Resistance of the electrolyte confined between two electrodes having unit cross-sectional area are separated by the unit distance. Unit cross-sectional area means the cross-sectional area is 1, and then distance between the electrodes are 1, unit distance. That is, the unit is different, meter or centimeter or millimeter, any one. Okay. Now the resistivity is defined as the resistance of an electrolyte confined between two electrodes having unit cross-sectional area and separated by the unit distance. Okay. The ratio L by A is called cell constant. Very, very important. L by A is equal to cell constant. The unit resistivity is ohm meter. The resistivity, this is very, very important 1-mark question. Resistivity is, what is the unit of resistivity? Ohm meter. Now conductivity, C is the conductivity for letter. It is more convenient to use conductance rather than resistance. It is more convenient to use conductance rather than resistance. Resistance with conductance is more important. The reciprocal of the resistance 1 by R gives the conductance of the electrolytic solution. The reciprocal means 1 by R. 1 by R is the conductance of electrolytic solution. The conductance is, the unit of conductance is Simon. Reciprocal value of the resistance is called electrolytic, conductance of the electrolytic solution. C is equal to 1 by R. Formula, C is equal to 1 by R, reciprocal value of resistance. Now C is equal to 1 by R. 1 by R substitute the R value substitute to this, C is equal to 1 by rho into A by L. R means already see that rho into L by A. This is substituted to reciprocal value for 1 by R. C is equal to 1 by rho. Again the R is interchanging numerator to denominator, denominator to numerator, 1 by rho into A by L. This is the formula for conductivity. Very, very important formula. Unit is Simon. The reciprocal of the 1 by rho is called the specific conductance. Here the 1 by rho is called specific conductance, conductance of the conductive of the resistance of the resistance, specific conductance of the resistance. The reciprocal of the specific resistance 1 by rho is called the specific conductance. Okay, this is represented by kappa. Kappa is the symbol for this conductivity, specific conductance. Okay, kappa. 1 by rho is equal to kappa. Substitute this value. 1 by rho is equal to kappa. Substitute this. The formula is kappa is equal to C into L by A. 1 by rho is kappa means C is equal to kappa into A by L. Now I want kappa. Kappa means this side, that is right hand left hand side, you bring the left hand side L by A. So kappa is equal to C into L by A. Understand? If A is equal to 1 meter square, area of cross section is 1 meter square, and L, distance between the two electrodes 1 meter, then kappa is equal to C. This is very, very important point. Unit, already in definitions, unit area cross sectional and unit distance, that is A is equal to 1 by 1 meter squared and L is 1 meter, then kappa is equal to C. Okay. Now the specific conductance. What is specific conductance? Specific conductance, already see the kappa letter. Kappa. What is kappa? Specific conductance defined as the conductance of the cube of electrolytic solution of unit dimension. This is the definition for specific conductance. Cube, conductance of the cube of the electrolytic solution in unit distance. The SI unit of conductance is Sm power minus 1. Sm power minus 1. This is the formula unit of this kappa. Kappa unit, Sm power minus 1. You see that the relationship kappa is equal to 1 by R into L by A. 1 by R into L by A into 1 ohm. This is the unit, 1 by ohm. This is the formula. Unit wise 1 by ohm into M divided by M square. So ohm per 1 meter, cancel it, M and M square, 1 M is cancelled, therefore ohm per minus 1, power minus 1, M power minus 1 is equal to, this is interchanging the letters, mho meter per 1 or Sm per 1. This is the formula for, this is very, very important formula for kappa. Okay, understand? Next, molar conductivity lambda M. Lambda, this is the letter for molar conductivity, lambda M. Lambda M means, what is lambda M? Molar conductivity. Solutions of the different concentration have the different number of electrolytic ions in a given volume of solution. Different concentration, different number of electrolytic ions given volume, in a given volume of the solution, they have different specific conductance. Therefore, the quantity called molar conductance is introduced. How to raise the molar conductivity? How to develop the molar conductivity? Because the solution, various solutions, we have different concentration and different number of electrolytic ions, that is chemicals, different types of electrolytic chemicals, through electrolytic ions. The volume of the solution, given volume of solution, they have the different specific. This means in a given volume of solution means all are same volume, constant volume. they have the different specific conductance. Therefore, the new concept molar conductivity is introduced, lambda m, lambda m. Now, a conductivity cell have the electrode separated by 1 meter. 1 meter already last topic, see that 1 meter, the electrodes distance 1 meter, having Vm cube of electrolytic solution. Vm cube means volume of the solution, Vm cube, 1 liter, 2 liter, 3 liter, any one. Volume of Vm cube. Electrolytic solution contains 1 mole of electrolyte, 1 mole of electrolyte. So, such conductance is called molar conductance, molar conductance. This is the definition for molar conductivity. 3 conditions are there. The distance between the electrodes 1 meter, volume is Vm cube, and the mole 1 mole of electrolyte, 1 mole of electrolyte. Condition is there. This conductance is called molar conductance, lambda m, lambda m. The conductance 1 meter cube electrolytic solution, 1 meter cube means volume, Vm cube is equal to 1. V is 1 means is called specific conductance kappa. Already see that 1 meter cube electrolytic solution, specific conductance kappa. Therefore, the conductance of mentioned Vm cube solution, lambda m, is given the following expression. The expression is given lambda m is equal to kappa into V, kappa into V. Kappa is already 1 meter cube. Volume, given volume, here the conductance of the solution Vm cube solution means lambda m is equal to kappa into V. We know that molarity, very important formula for molarity. Already seen that in ionic equilibrium also, same formula. Molarity, number of moles of the solute, number of moles divided by volume of the solution, V dm cube, decimeter cube. Dm cube means decimeter cube. N is the number of moles of the solute, volume of the solution, V in decimeter cube, decimeter cube. Therefore, the volume of the solution containing 1 mole of the solute, 1 mole of the solute. Here the number of moles is 1 mole, assume that 1 mole of the solute, 1 by m, that is mole per 1 liter, 1 liter per mole. We note that 1000 decimeter cube equal to 1 meter cube. This is the conversion table for meter cube to decimeter cube, decimeter cube to meter cube. 1000 decimeter cube is equal to 1 meter cube. This is the relationship, decimeter cube and meter cube. This is important for this formula. Now, volume per meter cube is equal to, from this formula, volume per meter cube is equal to 10 to the power of minus 3 divided by mole, number of moles, m. So, mole per mole meter cube, meter cube. Substitute the equation, this equation to equation 1. We get the lambda m is equal to kappa Sm power minus 1. This already know that kappa, this is a unit for kappa, kappa into 10 to the power of minus 3 divided by m. 10 to the power of minus 3 means already see that the solution containing 1 mole of solute in 1 liter, 1 liter divided by m, mole per mole per meter cube, per meter cube. Okay, understand? Third equation, first equation, second equation, third equation. The above relation defines the molar conductance in terms of the specific conductance and the concentration of the electrode. The above relationship deals the specific conductance of the and the concentration of the solute. Specific conductance means kappa, concentration of the solution means This is the concentration, 10 to the power minus 3 divided by mole. Okay. Now next, equivalent conductance lambda. Lambda m separately, and lambda is separate. Equivalent conductance. Equivalent conductance is defined as the conductance of Vm cube of the solution containing 1 gram of equivalent electrolyte. 1 gram. 1 gram, this is the constant value. The definition equivalent conductance means 1 gram of electrolyte. Conductivity cell in which electrodes are 1 meter apart. 1 meter. This is the condition. Distance is 1 meter and volume of the electron, volume Vm cube, and then 1 gram of electrolyte. 1 gram of electrolyte. Quantity 1 gram of. This is the definition. So the relation between the equivalent conductance and the specific conductance. Equivalent conductance is lambda, specific conductance is lambda m. So the formula is lambda is equal to kappa into 10 to the power minus 3 divided by n. Gram equivalent per 1 meter cube divided by n. Capital N. This is the relationship. Kappa is the specific conductance, N is the concentration of the electrolytic solution. Here introduce the concentration of the solution. Already 1 gram of the electrolyte is we taken. So kappa gram equivalent m cube divided by n. N is the concentration expressed in normality. N is the concentration of the in normality. Now next topic, factors affecting electrolytic conductance. Factors affecting electrolytic conductance. What are the factors affecting electrolytes? What are the factors? One is interionic attraction between. Interionic attraction. This is very, very important in chemicals. Interionic attraction between the oppositive charged ions of solutes increases the conductance will decrease. This is a main point in don't remember that in electrolytic solution. Interionic attraction means positive ions surrounded with negative ions. The attraction between positive and negative. These are the concept. Oppositively charged ion solutes increases. Attraction between the oppositive charged positive and negative ions or increases, the conductance will increase. This is already the basic principles. Next, the solvent